Have you ever considered that, while artificial intelligence can write these breathtaking poems and it can paint sweeping, hyper-realistic masterpieces and even recognize your face in a crowd of thousands, it essentially has no sense of smell.
Right, yeah, none at all.
It's like the most brilliant mind in the world is just uh, trapped inside a sensory deprivation tank or behind a thick pane of glass. It can see us and hear us, but it can't perceive the actual fundamental chemistry of the world we live in.
It really is a profound sensory bottleneck. I mean, we are building these incredibly sophisticated models of reality for our machines to operate within, but they are completely blind to the chemical environment.
Which is wild when you think about it.
It is, and considering how much of the natural world communicates and operates through chemistry, from food safety to environmental hazards or even just basic navigation, that is a massive gap in how AI perceives the physical world.
Which is exactly why today's Deep Talk is going to be so fascinating for you. We're looking at a state-of-the-art paper. It's titled EP381, Olfaction-Vision-Language Embeddings.
Yes, by Cordell K. France from Sentience Inc.
Right. And our mission today is to explore how AI is finally actually learning to smell. We're going to look at how researchers are tying raw chemistry to vision and language, how this creates a totally new wave of perception for robotics, and, what it actually means for you as these sensory devices start rolling out into the real world.
And we should probably establish right away that this is far more than a novelty.
Yeah, we aren't talking about a robot that just appreciates a fine perfume.
Exactly. This is a massive leap in constructing robust world models for artificial intelligence. By giving machines a functional nose, we are fundamentally upgrading their ability to navigate, understand, and, well, interact with physical spaces.
So, before we get into the actual mechanics of EP381, I think we need to understand the roadblock here. Why has this been so incredibly hard to do? I mean, from a layman's perspective, we've had chemical sensors for decades, right?
Oh, absolutely. The hardware's been around.
So why couldn't we just plug one into an AI and tell it to start smelling?
Well, the hardware isn't the primary issue. It really comes down to a fundamental data problem. Think about how we trained AI to see over the last decade.
Right, with massive data sets.
Exactly. Huge data sets like ImageNet, billions of images, meticulously paired with text labels. So a picture of a dog is explicitly labeled dog. A picture of car is car.
Right, we have an absolute abundance of that visual and linguistic data just freely available on the internet.
Yes, to train these models. But there is no ImageNet for smell.
Because, you can't just scrape the web for the smell of a damp forest floor.
Precisely the problem. There is no massive open source data set of paired image scent examples. You can download a billion pictures of a lemon, sure.
Yeah.
But you cannot download the precise chemical signature of a lemon interacting with a sensor and have it perfectly paired with that image. The data simply does not exist at the scale required to train a modern neural network from scratch.
Okay, so if the data doesn't exist, how on earth does EP381 solve this? Because the paper mentions making olfaction what was the phrase? A first-class citizen alongside vision and language in a single shared embedding space.
Yes, a shared embedding space.
But for those of us who don't, build AI for a living, what does an embedding space actually look like?
Okay, the easiest way to visualize an embedding space is to imagine a massive multidimensional map, sort of like a giant galaxy of concepts.
Okay, a galaxy. I'm with you.
And in this mathematical galaxy, things that are conceptually similar are placed physically close together. So the concept of a lemon is located very close to the concept of an orange, but it's millions of light years away from the concept of a submarine.
Right, that makes total sense.
And modern vision language models, things like CLERP or SIGLIP, they have already built this galaxy. They already understand that the text word citrus belongs in the exact same spot as a photograph of a lemon.
Okay, let's unpack this because this is where the paper just blew my mind. The AI already knows the word citrus goes with the picture of a lemon. It already has that map built out.
Yes, that heavy lifting is done.
So EP381 doesn't actually need to teach the AI what a lemon looks like or even what a lemon is?
No, not at all. It just has to teach the AI that a specific chemical molecule literally means the text word citrus.
It's using language as a bridge.
That is the core breakthrough right there. It connects the molecular structure of a gas to the descriptor word. And because the word is already mathematically anchored to the image in that giant galaxy we talked about.
The connection just naturally happens.
Exactly. The connection between the physical smell and the visual of the lemon naturally emerges. It's what we call a one-sided alignment. The researchers didn't have to spend decades in a lab pairing chemical sensors with cameras to teach the AI from scratch.
Because they leverage the web-scale knowledge that's already baked into the AI models we use every day. It's almost like language is acting as a universal translator between, say, a bloodhound's nose and a hawk's eyes.
Oh, I like that.
Yeah, because the bloodhound and the hawk, they don't speak directly to each other, right? They don't even perceive the world the same way. But they both understand the translator.
Right.
So as long as the bloodhound can describe the smell to the translator, the hawk knows exactly what to look for visually.
That is a perfect way to conceptualize it. And what's really fascinating here is that compared to the previous version of this technology, which was Collop 1.
Right, the first iteration.
Yeah, Collop 1 tried to forcefully train the smell and the vision at the exact same time. But this new method is far more elegant. By freezing the visual language backbone, meaning they lock that part of the AI so it can't change.
Oh, because protected.
Yes. They only teach the smell to align with the text anchors. By doing that, they preserve all that rich, pre-existing visual understanding while bringing a completely new sense into the fold.
Okay, so the AI knows how to connect a chemical signature to a word and a word to an image. But what does this actually look like for the user? Because, reading about the AI's internal geometry is one thing, but the practical application detailed in the paper, what they call aroma source localization.
Oh, it's incredible.
It feels like straight up science fiction.
The visual output really is stunning. Imagine you have a robot or even just a mobile device, and it's equipped with a camera and a connected electronic nose and e-nose.
Okay.
You point the camera at a scene. Let's say it's a messy laboratory workbench. The e-nose detects a scent in the air. The system then processes that chemical data, bridges it through language to the visual data, just like we discussed, and projects a color-coded probability heat map directly over your live video feed.
Wait, it literally paints the smell onto the screen.
It does.
So if it smells ethanol, it might show like glowing warm colors, reds and yellows, hovering right over a beaker of solvent while totally ignoring everything else on the desk.
Exactly. Or if you're in a kitchen and it smells eugenol, it lights up a pile of cloves, leaving the rest of the room cool and blue. It is quite literally making the invisible chemical world visible.
And it does this in real time, right? Which is where the specific architecture of the model becomes so important. Because the paper breaks down two main variants to handle this processing. There's Collop 2 Cloud and Collop 2 Edge.
Right. They serve very different purposes.
Let's talk about the size difference there. Because the paper mentions parameters, and I think we should define that. The cloud version is a 1.15 billion parameter model, while the edge version is only 101 million. What does a parameter actually mean in this context?
You can think of parameters as the artificial synapses in the AI's brain. They are the adjustable variables the model uses to make decisions.
Okay, so more is better.
Generally, yes. More parameters mean a higher resolution of understanding, a deeper ability to process complex, nuanced data. So Collop 2 Cloud is the heavy lifter. With over 1 billion parameters, it is designed for high-fidelity server action.
Makes sense.
It gives you maximum accuracy and very high-resolution heat maps, but it requires a massive amount of computing power.
Which a small roaming robot probably doesn't have strapped to its back.
Exactly. That is why the Edge model is the real star for robotics. At just 101 million parameters, it is highly optimized. It's designed for offline, real-time inference on simple processors or just small on-device graphics cards.
So it runs locally.
Right. When a robot is navigating a dynamic, fast-changing environment, it cannot afford the latency, the time delay of sending every single sensor reading up to a cloud server and waiting for the heat map to be beamed back down.
Right. If it's moving fast, it needs to know right now.
It needs to process that spatial data instantly, locally, on the device itself.
But wait, I have a question here. If I'm building that robot, I'm looking at a hardware market that is incredibly fragmented.
Oh, absolutely fragmented.
Yeah, there are dozens of different chemical sensors out there. You have metal oxide sensors that measure electrical resistance. You have acoustic sensors that measure sound waves passing through gas. Optical sensors, they all output wildly different types of raw physical data. Doesn't that break the system?
It usually does, yes.
Does a developer have to write custom code from scratch for every single sensor they want to plug into this AI?
That fragmentation is typically a massive operational bottleneck in robotics because a metal oxide sensor outputs a completely different squiggly line on a graph than an optical sensor.
Right.
If the AI only understands one type of line, it's useless for the rest. But to solve this, the sentience team built something called a chemical sensor encoder directly into the architecture.
Like a universal adapter.
Exactly like a universal adapter. The encoder sits between the physical hardware and the main AI brain. It takes all those wildly different, chaotic time series readings from literally any third-party sensor, and it normalizes them.
Oh, wow.
Yeah, it translates their raw physical output into a single, unified odor language that the Colab 2 model can natively read. So, as a developer, you don't need extra sensor-dependent software harnessing. The model normalizes the physics into mathematics for you.
Well, that removes a huge friction point for actually getting this into the real world. But as we know, any system relying on this delicate of a mathematical translation is bound to have vulnerabilities.
Definitely.
If the model relies entirely on this language bridge to connect smells and images, what happens when it encounters a totally new smell? Like if we try to teach it something new, doesn't that risk breaking the map it already built?
This is exactly what the researchers tested in their ablation study.
Right, the probing experiments.
Yes. An ablation study is where you systematically remove or alter parts of an AI architecture to see what causes the system to break. It basically tells you what each line of code is actually contributing. So they ran these probing experiments configurations C0 through C4 to see if they could aggressively fine-tune the AI to learn new chemical signatures without destroying its foundational understanding of vision and language.
So they're basically trying to stretch that language bridge without snapping it. And I know they introduced a specific mathematical constraint to handle this.
Yes, they implemented what they call a lambda guardrail. If you go back to our galaxy map, remember that the text anchor, say, the word smoky, is perfectly positioned to match the image of smoke.
Right.
If you start pulling on the word smoky to make it fit a brand new, slightly different chemical reading of smoke, you risk dragging the word away from its visual meaning.
Huh?
The lambda guardrail acts as a mathematical safety harness.
Okay.
It allows the model to map the new smell, but it artificially restricts the text anchors so they cannot drift away from their visual geometry.
I see. So it's less like a Jenga tower and more like a tightly woven spiderweb.
Yes, exactly.
The visual of the smoke and the word smoky are anchored together by a strong thread. If you aggressively pull the word smoky over to a new chemical smell without a guardrail,
Right.
you don't just stretch the thread, you rip the word entirely out of the web.
That is a much better way to visualize the tension, and we see exactly what happens when that thread snaps in configuration C4 of the study.
Which they call the over-fine-tuned state.
Right. They wanted to find the absolute boundary conditions, so they took the safety rails off completely. They disabled the lambda guardrail, increased the learning rate, and just let the model loose on new chemical data.
And what was the result?
Catastrophic collapse.
Wow.
That is the literal technical term used in the literature, and it is entirely accurate. In a single training step, the anchor drift, which measures how far the words moved from their original meanings in that galaxy map, plummeted. The text encoder experienced complete system-wide amnesia.
Wait, really? It just completely forgot how to map words to images.
Completely. The olfaction-language connection fell to near random chance. The grounding of images to descriptor words just broke. The general text-to-image capabilities of the entire multi-billion parameter system collapsed.
That is terrifying.
It is. But it proved a vital point about this specific architecture. Olfaction vision grounding doesn't degrade gracefully. It doesn't just get a little bit blurry or confused. If you pull too hard without the guardrail, the entire sensory matrix shatters all at once.
Okay, so if the AI's memory is that fragile, that creates a massive problem for a real-world deployment, right? A robot navigating a hospital or a factory is going to encounter weird, novel smells every single day.
Oh, constantly.
If it tries to learn those new scents on the fly, how on earth does it do that without triggering a catastrophic collapse and wiping its entire visual database?
This is where the paper transitions from theoretical AI architecture to really brilliant real-world infrastructure. To solve the learning problem without breaking the models, they introduced the Federated Learning and Observability System, or FLOS.
FLS, got it.
It is a framework designed to let a whole fleet of deployed instruments learn from each other continuously, safely, and crucially, without humans needing to manually label the new data.
Wait, how does a machine learn something new if a human isn't there to tell it what it's actually smelling?
It relies on a concept called prototypical networks. When a device out in the real world observes a consistent chemical pattern over and over, and its internal mathematics are highly confident about the structure of that pattern, that observation becomes an internal teaching example.
Like a baseline.
Yes, it's called a prototype. The machine is essentially learning from its own statistical confidence.
And to manage all these new prototypes, the system uses something called tricycle memory. It breaks the robot's memory bank into 3 distinct levels: local, global, and external. Can you walk us through how those interact? Let's say we have a robot working in a coffee shop.
Certainly. So the local memory is hyper-personalized to that specific robot. It holds the chemical prototypes that the coffee shop robot sees most reliably in its own daily environment. So the specific roast of the espresso, the exact cleaning chemicals they use on the counter.
Right, its own little world.
Exactly. Then you have the global memory, which is the generalized knowledge pulled down from the cloud. It is the pooled wisdom of every single robot in the entire network worldwide.
So the local robot knows its own shop perfectly, but it still benefits from the general knowledge of the global fleet. Where does the external memory come in?
The external memory acts as a consensus check. Think of it as a peer review system. Imagine our coffee shop robot develops a faulty sensor, or maybe someone spills a highly unusual synthetic perfume right on top of it, skewing its readings.
Okay.
If it just confidently uploaded that bizarre observation directly to the global model, it would infect the entire worldwide fleet with a bad prototype.
It would teach every other robot the wrong smell.
Exactly. So before an update goes global, the external memory allows a device to check its confident findings against a localized group of similar peer devices. If our coffee shop robot's prototype sharply disagrees with what every other robot in similar environments is seeing, the system flags the data as suspect and rejects the update.
Oh, that's smart.
Yeah, it prevents bad hardware from corrupting the hive mind.
Okay, I have to step in here and raise a flag on behalf of our listener. Because if I have one of these robots navigating my house or a smart device sitting on my kitchen counter constantly monitoring the air, I start getting really nervous about that data going to a global fleet.
Which is a completely natural reaction.
Right. Is this device uploading the exact chemical makeup of my living room? Like, is it sending the specific chemical signature of the prescription medication on my nightstand or the wine I drank last night to some centralized server?
That is a highly valid concern, and honestly, anytime we introduce a new sensory modality into the home, privacy has to be scrutinized. But the researchers address this directly in the FLOS architecture through a strict asymmetric privacy design. The system physically splits the data path.
What do you mean by physically splits it? It's not just a, software terms of service promise.
No, it is structural. The raw identifiable data, so the actual continuous environmental time series readings from the sensor that could be used to deduce your personal habits, those are encrypted and locked away in a localized store on the device itself.
Okay.
The global training network is structurally restricted from accessing it. The cloud can only access what are called de-identified mathematical latents.
And what exactly is a mathematical latent in this context?
A latent is a highly distilled, abstract representation of the data. It is literally just a set of coordinates in that galaxy map we discussed earlier.
All right.
It is not sending an audio file, or a video file, or a raw chemical graph to the cloud. It is simply sending a mathematical vector that says, I found a new pattern, and it belongs exactly at this coordinate relative to these other concepts. The cloud gets the abstract geometric lesson, but it never sees the raw personal data that actually taught the lesson.
Okay, well, that clarifies things immensely. The hive mind gets the coordinates, but my actual lifestyle habits stay localized on my device. Now, as brilliant as this entire architecture is, to be truly well-informed, we have to examine the blind spots. What can't COLIP2 do? Because the paper is quite transparent about where the foundation cracks.
It is, and the limitations are significant. The most prominent failure mode is that the system's grounding is only accurate at the family level. Because the model relies entirely on human descriptor words to bridge the gap, it inherently lacks the microscopic precision of a dedicated laboratory instrument, like a mass spectrometer.
So if it's scanning a kitchen counter and you ask it to find a lemon,
the heat map will very likely highlight the lemon, but the thermal projection might also bleed over and accidentally light up other citrus fruits, or even certain household cleaners in the frame that share a similar broad chemical profile.
right, it gets you into the right ballpark, but it does not give you pinpoint molecular accuracy.
Exactly.
Which means it also struggles with what AI researchers call zero-shot identification, right? where you ask the AI to identify something it has absolutely zero previous training on.
Correct. If the e-nose encounters a highly complex synthetic chemical substance that was never represented anywhere in its training data, it cannot magically deduce its molecular structure from scratch. Because it has no text anchor to attach it to, it might weakly associate the new smell with a known odor family, but it will fundamentally fail to identify the novel substance.
Because of that lack of molecular precision, there is a very explicit, heavily bolded safety warning in the paper that we need to pass along.
Yes, the Sentience team is adamant. This is a research prototype, not a certified safety device. The outputs we've been discussing, the heat maps, the descriptor matches, those are mathematically generated rankings and probability fields. They are not calibrated, exact measurements.
So to be completely clear for you listening, do not hook this AI up to your factory's ventilation system to act as a toxic gas leak alarm, and do not use it to decide if the raw chicken in your refrigerator is safe to eat.
Absolutely not. A high probability ranking for a scent on a heat map does not equate to a precise reading of concentration levels, nor is it a guarantee of human safety.
Which brings us to the final and perhaps most fascinating limitation of the whole project. The entire data set, the actual source of truth for this AI, relies on human odor lexicons, the words we use to describe smells. But human perception of smell is incredibly subjective.
It is a massive biological bottleneck. Human olfaction is highly concentration dependent, and the way we describe scents is notoriously inconsistent.
Right, what smells good to me might smell terrible to you.
Exactly. And the lexicons used to train these models were created by human sensory panels, which means they inherently carry the subjective physical limitations of the human nose. The AI is inheriting a taxonomy of smell that is based on our imperfect biology. The paper acknowledges this constraint, noting that the field is looking toward organizations that are trying to build purely objective mathematical taxonomies of chemistry that don't rely on human sniffers.
Which is such a wild concept to wrap your head around. So, looking at the big picture of this deep dive, we have unpacked a truly paradigm-shifting piece of technology today. We've seen how everyday language acts as the secret, universal bridge to finally give machines a sense of smell without needing impossible, non-existent data sets. We've explored how federated learning and tricycle memory allow a fleet of robots to safely share geometric knowledge without invading your privacy or, collapsing their own digital brains. And despite the current limitations, the family-level heat map bleeding and the reliance on subjective human lexicons, we are undeniably one massive step closer to artificial intelligence that can truly perceive the invisible chemical world around it. It is finally breaking through that pane of glass.
It really is a monumental step forward for machine perception. But if we want to leave you with one final thought to explore on your own, it is this. The entire premise of Call Up 2, its absolute greatest strength, is its ability to match chemical structures to human odor descriptors. Words we made up to describe our own biological experiences. But a robot's electronic sensor can detect chemical nuances, inorganic gases, and minute parts per billion concentrations that are completely invisible to human biology. So if we continue to constrain artificial olfaction to human language, are we actually teaching AI to smell the objective physical world? Or are we just forcing a superior sensor to experience reality through the tiny limited window of the human nose?